Hello guys and welcome back to my channel Interview with Bunny. So in our last two videos we have seen how to detect a cycle for an undirected graph with the help of the BFS and the DFS algorithm. And in this video today we will be solving the same cycle detection but for a directed graph. And the approach by which we will be solving the problem today is with the help of the DFS technique. So as I've already told you that detecting a cycle in a graph may not be a super complex thing to implement, but the concept is very crucial because with the help of this concept that how you can detect a cycle in a graph, you can solve multiple problems during the interview. So without wasting much time, let's start with solving this problem of how to detect a cycle in a directed graph with the help of the DFS algorithm. So over here, if you look carefully, this is an example of a directed graph. And I'm pretty much sure that after going through all the previous 11 or 12 videos, you are right now pretty much comfortable to understand that what is a directed, what is an undirected, and all this basic concept of the graph. So knowing this fact that this is a directed graph and how this is implemented, let's proceed further. So here if you look carefully from 1 to 2, there is a path. Similarly, from 2 to 3, there is a path. Similarly, from 3 to 5, there is a path. And from 2, there is again another path that is from 2 to 4 and 4 to 5. And from 2, there is another path that is 2 to 7, 7 to 8, 8 to 9, and 9 to 7. So from 2, there are actually 3 directions where we can travel. So in this complete graph, we have to find that whether there exists a cycle or not. So let's first understand how to detect the cycle manually in a graph. After that, we will see with the help of the code and the logic and the intuition that how we should solve this problem. So let's proceed with the manual approach. So over here, if you see, we are right now at node number 1. And from node number 1, we can easily travel to node 2. And from node 2, we can travel to node 3 and node 5. And from 5, since there is no outbound direction that is present over here, so this is the end of our traversal. Now what we'll do, we'll again go back to node 2 and we'll see what are the other direction that is present. So from 2, we can go to node 4. And from 4, we can again go to node 5. So here if you look carefully, we can reach the node 5 from 2 possible directions. One from this direction and another from this direction. But this is not a cycle. But if you remember, when we were solving the same type of problem for the undirected graph, in that case, this was a cycle because in case of the undirected graph, there was no direction associated over there. And that's why we can consider this entire thing as a cycle. But for the directed graph, this scenario is a bit different. So for this case, this is not a cycle. So let's proceed further and let's check that whether there exists any other cycle or not. So what we will do, we'll again go back to node 2 and from node 2, we'll see what are the other direction over here. So here you can see from node 2, we can go to node 7. From 7, you can go to node 8 and from 8, we can go to node 9 and from 9, you can go to node 7. And here if you look carefully, once we reach node 7, you can see we have already visited node 7. And here in this case, we are traveling in a same path that is clockwise over here. And we came to the same node on the same path. And thus in this case, this is actually a cycle. So the fundamental intuition is like, if you are encountering the same node twice and you see that you are coming on a same path, then that causes a cycle in the graph. So I think this is clear that what is a cycle in a directed graph. Now, since we have understood the definition of what is a cycle in a directed graph, let's now see with the help of the DFS concept that how we can solve this problem. So let's start with the approach of solving this problem with the help of the DFS concept. So with the assumption that you have gone through my earlier video, let's proceed with the DFS traversal for this graph. So as you know, the way we do a DFS traversal for a graph is with the help of the recursion technique. And whenever we are telling about the recursion, which means that you have to draw the recursive tree. So similarly over here also, we will do the DFS traversal with the help of the recursive tree. So let's start with the DFS traversal from the node 1. So we are starting our DFS traversal from node 1 and here we will check from node 1 what are the direction associated over here. So here in this case you can see the direction that is associated over here is from node 1 to node 2. So we will go to this path. So from node 1 we will go to DFS of 2 And also we have to maintain a visited set, just the way we do the DFS traversal. So we will consider a set called as visited. So once we were at node 1, we have marked it as visited. Similarly, when we reached node 2, we are marking it as visited. Similarly, from node 2, we can see there are three paths that are present. One is from node 2, we can travel to node 3. From node 2, we can travel to node 4. And from node 2, we can travel to node 7. So there are three paths where we can travel from node 2. So let's cover them one by one. So let's proceed with this path, that is from node 2 to node 3. So we'll call the DFS of node 3 and we will mark it as visited. From node 3, what are the neighboring nodes? That is node 5. So we will take this path, means from node 3 we came to DFS of 5 and we will mark it as visited. And from node 5 we will check what are the neighboring nodes or where it is heading towards. And here you can see node 5 doesn't have any outbound direction, means we are not heading anywhere from node 5. So this is the dead end for this complete path. So as a rule of the DFS and the base case of the recursion, what we will do? We will return from here. So we will do a return from here. So from node 5, we will return back to node 3. And here we will again check whether there is any unvisited path or not. So here you can see there is no unvisited path. So we will again return back. So from node 3, we'll go back to node 2. So again at node 2, we'll check whether there are any unvisited path or not. And yes, there are some unvisited path present over here, which are node 4 and node 7. So let's cover the next path, that is from node 2 to node 4. So from node 2, we will call our next DFS function, and that is DFS of 4. And we will mark it as visited. And similarly, from node 4, we will check what are the neighboring nodes for the node 4. And here in this case, we can see the neighboring node is node 5, but this node is already marked as visited, means we have already gone through this path. But check this point. If we are traversing from node 4 to node 5, this is in this direction, but this is not a cycle over here, which means that only with this point that once we detect a visited node that will create a cycle is not true, because here you can see this path is actually crucial to prove that there exists a cycle or not, because here you can see from node 2 we can arrive to node 5 from both the direction, but this is not creating any cycle, right? So somehow we have to capture that from which path we are actually traversing. Because as the cycle detection algorithm suggests, if we are visiting the same node on the same path, then only we can prove that there is a cycle for the directed graph. So to prove this point and to create this algorithm, we need some additional thing. That is, we need a data structure to conserve or maintain this path. Means somehow, once we are doing this traversal, we also have to capture that from which path we are coming. And if we see that if a same node is there, which is already marked as visited and it is on the same path, there only we can say there exists a cycle in the directed graph. So I hope you are clear with the intuition that why we need an additional data structure to maintain that which path of the DFS we are following. So with this concept in mind, let's see how to implement this logic of detecting the cycle for a directed graph. So let's now start again this DFS algorithm, but with some additional data structure, and let's see how easy it is to solve this problem. So as we just discussed, we need two data structure. One is a visited set and another is a path set. Now we'll do the same thing, that is the DFS traversal. And as we know, we will start with DFS of 1, that is the first node, and we will mark it as visited. And also we have to update this path variable, which means that we are starting a DFS algorithm which start from the node 1. Now what we'll do, as we do the DFS traversal, from node 1 we will go to the node 2. So we are going to the node 2, we will mark it as visited, and we will update this path array also. So here you can see we are keeping track of in which path we are traversing. So here you can see from node 1 we have traveled to node 2, means we are following this path right now. Now what we'll do, from node 2 we'll go to the node 3. So DFS of 3 is there. Now we'll mark it as visited and we will put it in the path variable. So here you can see we are in this path from 2 to 3. So now what we'll do, from DFS of 3, we will call DFS of 5. So we are now at node 5. We will mark it as visited and we will update the path over here. So we are right now following this path. So here you can see once we are at node 5, you can see this is marked as visited. And here if you see the path value, you can see exactly which path we are following. Now what we'll do here, you can see node 5 does not have any outbound edge. So we have to return back. And here, once we are returning from node 5 to node 3, here we have to update our path variable. Means since we are done with visiting node 5 and we are going away from node 5, means we are right now at node 3, we will remove this entry over here. Means the node 5 will get deleted from the path variable. Means right now we are over here, that is at node 3. And you can see how we reach node 3. We have followed this path, that is 1, 2 and 3. So the key point is like whenever you are backtracking this recursion tree, in addition to only return from this function, you have to also update the path values. So that is the basic concept of how we will be implementing this algorithm. So let's do it for a few more. It will be very easy to understand. So what we'll do, we are right now at node 3 and you can see from node 3 we cannot travel in any further, right? Because node 5 is already visited. And here if you look carefully, we are not deleting from the visited state because the node is already marked as visited, but we are just only updating this path variable. That is the only operation that you have to do, because if you are also removing it from the visited state, then there will be an infinite loop that will be running. So we do not want to do that. What we need to conserve the path only. So what we'll do, from node 3 we will return back to node 2. So from node 3 we'll go to node 2 and we will also remove node 3 entry from the path variable. So we will remove node 3 from here. So right now we are at node 2. Now what we'll do, from node 2 we will do our traversal, that is we'll go to node 4, and here from node 2 we'll do a DFS of 4 and we will mark it as visited, and also we will put it in our path variable. So right now you can see we are following this path, that is 1, 2 and 4. I think this is clear right now. Now from 4 we will do the next DFS, that is node 5. But here you can see node 5 is already marked as visited and there is no entry of this node 5 in the path variable, which means that we have already visited the node 5, but it was some different path. It was this path which is not a part of the cycle, and hence we prove that this node 5 which is already marked as visited, but it is not a part of the cycle. So what we'll do, since it is already visited, we do not have to do a DFS traversal over here. What we'll do, we will return back. So from node 4 we'll return back to 2, and also we will remove it from the path value. So node 4 is deleted from here. Now it's simple. What we'll do, from node 2 we'll go to the node 7. So from node 2 we will take another path, that is DFS of 7, and we will mark it as visited, and also we will put it in our path value. Path 7 comes over here. Now from path 7 we have to go to DFS of 8. So we'll mark it as visited. So we are now in this path. We will mark it as visited and we will put it over here. So we right now are in this path, that is 1, 2, 7 and 8. Now what we'll do, from 8 we will again do a DFS traversal, that is DFS of 9, and we will mark it as visited and we will put it over here in the path value. So we are right now at node 9, and from 9 now comes the important thing. Now from 9 what we'll do, we will do the next DFS traversal, and that is DFS of 7. But here if you see, this node, that is node 7, is already marked as visited, and this node is also present on this path value, which means that we are encountering 7 twice moving on the same path. And that is true, because if you see from node 1, once we are traversing, we have encountered 7 over here. Again from 9 we are again encountering 7 over here on the same path itself, and thus this creates a cycle over here. So the key concept is like, whenever you are doing a DFS traversal, if the node which you are going to encounter, if that is present in the both the visited set as well as in the path data structure, we can say that there is a cycle present in this graph. This is the basic logic and the algorithm to detect a cycle in the directed graph. I hope this is clear. And believe me, the implementation and the code is pretty simple. It will just take hardly 2 to 3 minutes to understand the entire code to you guys. If you are familiar with the way or the pattern how we are coding in the last 11 to 12 videos. So let's start with the implementation of cycle detection for a directed graph with the help of the Java code. So here we are again back with our online Java compiler. Here you can see we have created a graph object, and here this is the graph class. So these are the pretty much the same code that we are using for the last 12 video. So I hope I do not need to explain it again that what we are doing over here. Only thing that you have to remember is since it is a directed graph, so you have to just update the adjacency list accordingly. So there will be only a single entry, means there is a path present from node U to V, but not from V to U. So we are updating it only once. I hope this is clear, which I have already explained it in my third and the fourth video. So this is our graph class, and here if you see, this is the graph object that we have defined, and this is the same representation of the graph that we were discussing right now. So we are done with this two step. Now what the next step is like, we have to call the function that is the detect cycle with the help of the DFS. So I've created a function called as detect cycle DFS. So let's see what is there. So this is the same code that we have used for the last two videos for the cycle detection for our undirected graph using the DFS and the BFS approach. So this is the same code. The only change that I have done is I have defined an additional data structure called as set, which is nothing but this path set. You know why this is important. And here in this function, that is cycle DFS, which is the main function, we are simply passing this path variable as a parameter. So that is the only thing. Rest everything is similar, just like our last two videos. Now the main thing, that is the implementation of this logic. Let's see one by one. So this is the total complete code that you need to write to find out, that is whether there is a cycle present in the directed graph or not. So let's see what we are doing. So as you know, DFS traversal is a recursive call. So let's see what we are doing within this recursive function. So what we are doing, we are calling the function that is cycle DFS. And here what we are doing the same thing that we do for a DFS traversal. That is, we are first marking the node as visited. So here you can see this is the node that is the starting point, and we are marking it as visited. And here the additional thing that we are doing is we are updating our path variable. So as we have discussed, we are inserting the starting point or the node in our path variable. Means we are going through this path. Now what we are doing the same thing. We are checking what are the neighboring nodes present for this current node. Now what we have to do, so as a rule of the DFS says, we have to iterate over each and every nodes, and we have to traverse all the paths that are present. So what we are doing, we are iterating over this connected node array list. And here the first check that we are doing, that we also do for the DFS traversal, we are checking whether the node is already marked as visited or not. And if it is not marked as visited, what we are doing, we are simply calling the DFS functionality again. So here you can see we are again calling the DFS functionality from here if the node is not visited. But if the node is visited, we have to check whether there is a cycle present or not. And how we are checking? If the node is visited, we have to also check whether the same node is present in the path variable or not. And if both the things are true, means it is visited as well as it is present on the path variable, means we have detected a cycle, and thus we are returning true from here. I think this is clear how we are doing this traversal, and this is the only additional check that you have to do to detect the cycle for a DFS traversal. And if there is no cycle present in this graph, means it is a simple DFS traversal, means we will keep on iterating over here. And once we are at the terminating node, means there are no further neighboring nodes present over here, means when this for loop will end, there what we'll do, we have to return back. As we were just discussing, once we were at node 5, we have to return from node 5. So at that time, what we were doing, we have to just remove that node from the path variable. And we are confirming it that this path does not have any cycle. And that's it. This is the only 10 to 15 lines of code that you need to detect a cycle for a directed graph. So let's run this algorithm and hopefully this will work. So let's click on run. And great, here you can see we have detected a cycle over here. And if you remember, this is the node that is actually causing this cycle because there was a connection from node 9 to node 7. So let's omit this path from the graph and let's see whether still there exists a cycle or not. So if I click on run, you can see this returns false, means there is no cycle in this graph, means our algorithm is running completely fine. So I hope you have thoroughly understood this video and you have found this video useful. And if you have found this video useful, do not forget to like, share and subscribe to my channel and hit the bell icon so that you never miss an update from my channel and you are always ready for your next interview. And in our next video, we will solve the same problem, that is detecting cycle for the directed graph but with the BFS traversal. And believe me, that is very important because over there, to detect a cycle with the help of a BFS algorithm for a directed graph, we will be learning couple of important algorithms that will be very important, very important for your technical interview. So without wasting much time, let's go to the next video where we will see the next topic, that is the cycle detection for a directed graph using the BFS traversal. So see you on our next video. Thank you.